So today is 6th lecture, right? Is my screen visible to all of you?
Yes,
Yes,
sir.
sir.
Good. Okay, so we have seen lot of things in this course so far. EN 203 Digital Electronics and Circuits related to the what is digital and what is analog, why it's needed, what we are trying to do in digital, and we have come up with some rules in the previous class, so that we will quickly review, and then we will go to next level of understanding about the digital. So we have seen that there are two very important conditions for digital to exist, and these are the most basic postulates or rules, whatever you want to call, that X can take, or any Boolean variable or switching variable can take either 1 or 0, only one state at a time. It cannot be both, or it cannot be in between something. So this is the most important principle on which this whole digital electronics exists. Of course, we will see some exceptions also, but as of now, when we are discussing the rules and principles, we assume that this is true, irrespective of the practical constraints. Now, Boolean algebra, when we say, it is basically combination of these two states and three operations. So anything we want to do in this Boolean algebra or switching algebra or any of the digital design, we have these three operations essentially being performed, which is sum, which is called as or, product, which is called as and the not operation, whether you relate it or represent it with a bar on the variable or with a prime next to the variable. So these three functions we will use. So first two are multivariable operations, and the last one is monovariable or univariable operation. And with this we will perform all our operations whatever are needed. So we have understood what is AND operation, what is OR operation, NOT operation, all these things we have understood, how to represent it in terms of symbols. So we have seen symbol for AND gate, OR gate, NOT gate, these things. These are the basic operations. Anything coming on top of this will be a combination of all these. So then we understood what is truth table. So basically whatever values we are giving for the variables 0 or 1, these are called truth values, and the possible combinations when we work out and put out the output of that particular function or particular circuit, that is called the complete exhaustive table, is called truth table. Then we have seen some more things, that if we add the same variable to itself, if we multiply the same variable to itself, then it remains same. So, and if we add 1 to a variable, or take product with 1 with the variable, or take sum with 0 or multiply with 0, so what are the outcomes that we have seen? Then some more simple rules we have understood, and these all can be proved through the laws of induction. So we can make the truth table and we can show that yes, all these things hold true. So we can prove it in that manner. Another identity what we have understood is that if we add any number with its complement, then it's always 1. And if we take product of a variable and its complement, it is always 0. So with this we have understood the duality. Duality basically means if you are representing a function and with some variables and operations, and you have to take, okay, I think yes, and you have to take the complete not of that complete function, then you can replace all the existing variables and the numbers and operations with their dual, corresponding duals. So we also saw De Morgan's theorem. So this is what is generalized over here in terms of a function, and this is utilized basically to solve one of the examples which we discussed last time. So we can see that such a big expression, but finally it boils down to 1. So if we appropriately use these theorems, we find that this function written as with so many variables, so many operations, is actually always true. So there is no other value for this. So simplifications like this can be done using all these theorems. Now, let us try to understand, if we are given a truth table or if we are given a function, how do we realize it? And not only with the theoretical gate symbols and all, but how to practically realize that using the this electronic devices and other things. So now in few next classes, we will discuss all these things in much more detail. So for example, if I take a function with three variables, let's say I write the truth table for this function. So all the possible combinations we can write. So how many possible combinations would be there?
8.
Yes.
8.
Correct. Now the function f may be true for few combinations and it may be false for all other combinations. For example, if it is true for all 8, that means it's simply f equal to 1. We are not talking about that condition. What we are talking about is this function is true for only few combinations. For example, if I say that it is true here, or it is true here and here, and for all other combinations it is giving a 0 value. So this is one typical example of how a Boolean function or Boolean circuit or something will look like. So this is what we are trying to realize. Now if you are given this truth table or any function is given and you can make the truth table, how do you realize this? So both the things are possible. Either you can go by putting some logic. No, you can think yourself that what is happening in this circuit. The function is 1 for only these three combinations, which means we can think about OR operation of these three terms. So whenever this combination is coming, it is 1. Whenever this combination is coming, it is 1. Whenever this combination is coming, it is 1. All other places it is 0. So some kind of OR operation happening between the three possibilities. Isn't it? As simple as that, we can think. Now, if you see closely for the last two, here, whenever this x and y, these two variables are 1, irrespective of the value of z, this is 1. Understanding my point? So another way we can say that whenever this a, x and y, this is true, our function is true, irrespective of z. So basically last two conditions we have combined in just one. So this is one way to see. Now here we are left with only two options. So what is the first option? It says that whenever x is 0, y is 0 and z is 1, then it is 1. Or whenever both x and y are 1, it is 1. Whatever is the value of z. So we will realize in this combination form only. Let us say first you realize the last two terms. So you can write x and y, and of course the operation happening over here is AND, because both has to be true, right? Correct, right? So this is giving one condition, these two combined. Now the third is giving that whenever z is true, or I am putting a not over here before the next AND gate, or sorry, not or but AND. So whenever z is 1 and x is 0 and y is 0, then again this is giving another possibility when the function could be 1. Understanding my point? And when either of the conditions are true, we actually get to have this function equal to 1. If either of the conditions are true. This is what the truth table has also said. Understanding my point? Yes or no?
Yes, sir.
Any confusion in this? Anyone? Any confusion?
X, Y, and Z all are taken in the AND.
Say again. I did not hear.
So X, Y, and Z all three are taken in the lower AND gate.
Yes, which is what we are doing this condition. So you can say, right, whenever
Yes.
any zero is appearing for a true value of function, then we write it as not, x not, y is also appearing as not, so 0, so y not, and z is true, so z is coming as z. So if, let us say, you are trying to write the function, what actually the function is, you can write these things, these three terms as sum. So x prime, y prime, z plus the second condition where it is true is x, y, z prime, and the third condition where it is true is x, y, and z. So here also, if you see, these two terms can be combined very easily. Z plus z prime is always 1 if you take xy common. So essentially, whatever way you go, we will be able to realize, even without knowing much about the digital circuit or even knowing much about how to minimize the function, how to get the best possible circuit which is optimized in terms of resources and all. It's okay. Still, we can have a good realization of any digital circuit based on our understanding whatever we have gained so far in the course.
Sir,
Yes.
directly xy plus z will be enough, no, sir?
Say again.
X dot y plus z will be enough, no, sir, for that output.
X dot y
Plus z.
is that true? If you simplify, yes or no? Okay, so maybe you take it as an exercise. Prove through that lookup table or
No, sir.
huh?
No, sir, no, sorry.
No, true, sir.
It's not.
Is it true or not? Yes or no?
No, sir. No, sir.
Okay, let us check all the three conditions whether it is giving the true value or not, and all other conditions must also be 0. It's not like it has to give true for only those conditions. It has to be false also for any other combination. So let us use this combination 001. So what are you getting? 1, which is true. Now if we use this combination
0, 1, 1. If it becomes
110 or 111, then must be 1, and here also it must be 1. So yes, it is giving correct value for these combinations true, but is it giving 0 value for any other combination? For example, let us take 011.
It's not satisfying.
So it's still giving 1, whereas it must have been 0. So then this is not true. This is what I'm trying to point out. It not only has to satisfy these three conditions, but it has to satisfy all other combinations as well. It has to be false for any other combination. Understanding my point?
Yes, sir.
yes.
So this is what we have to ensure. So this is one way like how we can realize. So when you are doing your practicals tomorrow, I will explain little bit more what you have to do in that. But this is one general way. No, anybody who has got little bit understanding of digital circuit can do. Now, at this point of time, I want you to understand little bit more about how we are realizing these things practically. Practically, when you say what is AND, what is OR, practical means you are having some physical devices, not just some symbols drawn on paper or some program written or something like that. So some physical devices which are connected in that manner, which are obeying these rules. This is what means. Yes. So this is what we have to understand now. So of course, I have said in the beginning that anything, whatever we are doing theoretically over here, are actually realized through the electronic devices or semiconductor devices. So what are these devices? Can you name few?
Combination of some transistors.
No, you have to name the device, not combination and all that. That we will go later on.
Diode.
Yes, most basic semiconductor device which we must be aware about is diode. Then what next?
LEDs.
No, LED is again a diode itself.
BJTs.
BJT.
MOS.
Yes, that is bipolar junction transistor. What else?
FETs.
Hmm?
MOS.
MOSFET.
Yes.
MOSFET.
MOSFET, so field effect transistor and metal oxide semiconductor, whatever you want to call it. But essentially, this is the keyword, field effect transistor. So there is some difference between bipolar junction transistor and field effect transistor. We will see. There are some more, but for the digital electronic circuit, these three are more important. So in combination with some resistance and then sometimes some capacitor and all that, we realize all our digital circuits. Now, how are we doing this? What are the properties of these devices which are allowing us to go for these kind of circuits, no? Which enable us, or you can say, no, gives us the liberty to form such circuits and or in all these kind of operations. So first, let us talk about diode. So what do you mean by diode? What is diode?
Combination of two types of extrinsic semiconductors,
Okay, what two types?
P-type and N-type.
Yes. So basically here, if you have a silicon substrate and you dope with the P-type and N-type substrates, so essentially you end up having this kind of combination, a P-N type of silicon substrate. And when you keep this together, so what happens? This forms a very special kind of device which is called as PN junction diode. Basically, this forms a junction over here wherever it meets. A barrier is created. So some things you must have learned in your electronics class and in the previous classes, even with the class 12th curriculum also. So those things are true. There is no problem at all in that. So your understanding is perfectly fine. Now there are conditions when this diode can be made conducting and when it can be made in a blocking state. These are only two possibilities, right? It can either conduct or it can block. Understanding my point? So these two states essentially we take as on and off states. Yes or no?
Yes, sir.
Yes, sir.
Okay. Again,
Yes.
those who have turned off their camera, again turn on. And those who have not turned on so far, again I'm telling you, turn on your cameras now. If you are at home, doesn't mean you will stop responding during the class. Okay, now can you tell me the condition? Okay, maybe first we can just to revise, this is the symbol what we use for the diode. So the P type is represented like this and it is like this. So when do you say that diode is conducting and when do you say the diode will not conduct?
When current flows from P to N, it is conducting.
Yeah, when does it flow?
When
Forward
it's
bias.
forward
P is
bias.
higher than N.
When P is at higher potential.
So two conditions we are seeing over here, forward biased and reverse biased. So what is the meaning of forward biased? For example, if I have a circuit, let us say something like this, and another circuit I connect diode in other direction. So this is R, this is V. So can you tell what is the current in this circuit and in this circuit?
In first I and in second 0.
0
Say again.
V by R into left
V by R.
By R and
V
So
by
here
R.
it is V by R and here it is 0. So
Zero.
why do
Zero.
you call, why do you say that in first one it is V by R and why do you say it is 0 in the other one?
First is forward bias.
We considered the ideal case of diode where it is a short circuit.
Yes. So whenever you conduct or you have the polarity across this diode coming as positive in this manner, the P is having more voltage, more positive voltage compared to the N side. Then we say that diode is forward biased. It is ready to conduct. And whenever this is reverse, we say that the diode is reverse biased, which means it cannot conduct. It will be blocking this voltage. Of course, there are some diodes which do conduct in the reverse direction also, but they are used for different circuits. I will come to that shortly. So here when we are saying this is conducting, we assume that once conducting, it is like a dead short circuit. There is nothing across it. And so the circuit contains only the voltage and the resistance essentially. And so the current is dictated by these two parameters only. Whereas in the second circuit, when the diode is reverse biased, it is not allowing the voltage to cross its barrier. It's not allowing the current to flow through it. So what will happen? If it doesn't allow any current to flow through it, then I is actually 0. So all this voltage V, what is there, that will appear across the diode. There is no drop across the resistor. Understanding my point? In the first case, we had 0 voltage drop across the capacitor, across the diode, in the ideal condition I am saying. And the complete drop was taken by this resistance. Clear?
Yes, sir.
Yes, sir.
Simple thing, right? Now let us see what this basically means in terms of ideal characteristic. So when we are talking about ideal characteristic of diode, the VI characteristic, when we talk about VI characteristic, so what do we say? That the moment this is voltage across the diode, we take in this polarity, positive and negative, this is V. So whenever we are talking about the voltage going slightly positive, this is for ideal diode. So we are talking about the ideal characteristic. So whenever we say that this is ideal diode, the moment this V is slightly greater than 0, just V is 0 plus, slightly higher, it conducts. And ideal diode may carry any amount of current. So what we will say that the characteristic will essentially lie on the y-axis for any higher value of any positive value of V, and there will not be any drop across the diode. And the moment we go for a negative value, there cannot be any current. The diode will block any amount of voltage, so the characteristic will completely lie on the x-axis. Getting my point? This is what the ideal characteristic of diode is. So it is blocking any amount of negative voltage and it is conducting any amount of positive current. However, the practical diode, of course, will deviate from this ideal characteristic. Okay, let us draw in this only. Where would it deviate? First of all, it will not start conducting for just above zero value. It will take some more voltage for the diode to conduct. And current will not just vertically rise, it will have some more slope. So gradually it will rise. This is the first deviation, and this is what, wherever it is stopping, some average value you can take, this we call as forward voltage drop of the diode. So it could be 0.6 volts or 0.7 volts or something like that. And there is some slope also in this. It's not perfectly vertical line. There is some slope. We'll come back to that. Now coming on the negative voltage side. So yes, the diode behaves in a very ideal manner up to certain voltage. Then after that, what happens?
Breakdown.
Yes. Any material you take, even insulating, you keep applying a voltage across it. Even air, I am saying. After a certain point, it will break down. It will get ionized and it will break down. So this is property of any material. It cannot keep blocking infinite amount of voltage. So what happens after that? It will follow this ideal characteristic to a large extent and then it will finally break down. So when breaking down, there is suddenly huge amount of current flowing. This slope is much steeper compared to this slope. And this is what we call as breakdown voltage of the diode. So the breakdown property we exploit in the diodes called as Zener diodes, where we intentionally keep this value low. So sometimes maybe 3 volts, not 3.3 sometimes, or 6.6 volt or something like that. We make it like this, that it breaks down at 3.3. So in that manner, it ensures that the voltage is clamped at these values, whatever it is breaking down at. So there is different use for this property, what we have seen, the breakdown property. But here we are not going to use this breakdown property. We are going to use two different things. One where it is blocking and another where it is conducting. Understanding my point?
Yes.
Now, let us see. This is ideal and the real characteristic what we have drawn for the diode. Now, what about the equivalent circuit? Let's say when diode is there in the circuit, let's say in the previous circuit, ideally we are shorting it and ideally we are opening it. That is true. But practically that's not the case. There must be something more associated with the diode. It cannot be a simple wire shorted at two ends or shorting 2 points in the circuit. So let us first talk about the off state. So you clearly understood, right? This is the off state what we are talking about. And this is the on state what we are talking about. In between there is some ambiguity. We will not operate in this zone. So either our voltage would be sufficient, big enough to break this barrier and conduct, or it will be small enough that it goes into off mode very quickly. Clear? Yes or no?
Yes, sir.
Yes.
Now let's talk about the off state. So whenever our diode is having this voltage, let's say P less than some 0.6 volts or 0.7 volts, we say that it is in the off state. In this case, it is not conducting. Apart from some very small leakage currents, maybe some microampere, nanoampere currents flowing through this, that is very, very small leakage current, which can be ignored many a times. Apart from that, the diode can be seen as perfectly open circuit, which can take a good amount of voltage across it. Anything less than this, up to the V barrier or V breakdown. Understanding my point?
Yes, sir.
Fine. This is equivalent circuit of diode when it is in off state. Now, what happens when it is conducting? Which means when this voltage V is greater than 0.6. I'm not saying equal to, because equal to there could be some ambiguity whether it will conduct or may not conduct. So we strictly go for greater than 0.6 or 0.7, whatever is the threshold voltage. So in this condition, what happens? The diode conducts, and we know that it has some slope. So how do you model this diode during the on state? So what we do, we first put our barrier voltage or threshold voltage. So direction of conduction you have to consider. This is the way where current is flowing. So it is a reverse voltage. This is what your threshold voltage or 0.6 volts is there. This is blocking. Whatever you apply over here, this will be subtracted from it in the direction of conduction. And then there is a resistance. So this forward voltage drop, and this we can call as forward resistance. This is how diode is modeled during the on state. This resistance RF, what we are writing, it could be anything. Let's say sometimes even 20 ohm, or it could be as low as some 0.1 ohm or anything. That depends on the application and the manufacturer. If your diode is supposed to carry a lot of current, let's say 10-20 ampere, you cannot afford to have 20 watt or something like that. That's a huge power drop across this this thing getting exhausted across the diode, getting dissipated across the diode. So we cannot afford to have that. So the diodes which are used for power applications and all, they have very, very small voltage, this resistance over there. Understanding my point? For diodes which are used in our digital circuits and all other applications, where we are having huge resistances, let's say of the order of 10K or 20K already in the circuit. So this 10-20 ohm is actually nothing in front of that. So it can be very easily ignored. Okay, and here the current requirement is also few milliamps. So we are not carrying lot of current, and the power loss is also within the limits of the design. So this is how these values are. Getting my point? Yes or no?
Yes, sir.
Yes, sir.
Now, let us try to design our AND and OR logic using this diode circuit. So that will give a glimpse. No, it's not something which is used practically, but it gives an idea about what do you mean by AND circuit and OR circuit practically. So let's say if I have to draw the AND circuit, I can draw something like let's say this is the supply voltage 5 volts, some resistance R, and these are our two inputs X and Y. So the voltage at this node could be Vx, the voltage at this node could be Vy, and this is our output node Z, where the voltage could be Vz. This we call as our AND gate. Understanding my point? Now let us see how it works. So before that, maybe before getting into this gate, we must understand what is the logic that we are going to follow. So logic means we have to clearly define the voltage levels which we consider as 1 and the voltage levels which we consider as 0, and there should be some margin in between the 0 and 1 state. So let's say we are talking about the signal level, which means the voltage what we are going to see. So Vx, Vy, whatever is there, whatever inputs are there. So there could be 3 levels in this: 0 to 2 volt, 2 to 3 volt, and 3 to 5 volts. The first state 0 to 2 volt, any voltage between 0 and 2, we designate that as low logic. Anything between 2 and 3, we say this is our noise margin. We do not consider it as either low or high. and any voltage coming between 3 and 5 we call as high. So our binary logic value is 0 for this 0 to 2 volt and is 1 for 3 to 5, and here in this zone it is undefined. Understanding my point? This is the logic followed for the diode based circuits, which we can call as diode logic. So purely with diode and resistance we are trying to come up with some gates, and we are trying to come up with circuits which can be seen as gates or some other combinations. So we will see what are the advantages, what are the problems. So advantage, we can see these things are very, very simple. Now let us say, when I am saying that this is AND gate, what do I mean by AND gate? So let us say if we give some 4 volts at this value Vx equal to some 4 volt and Vy also equal to 4 volt. So of course 4 volt comes in what? Positive logic or high logic, right? So what we should expect is that here also our output should be high. That means anything between 3 and 5 volts. Now if we apply 4 volts at both these places, what would happen? Can you explain?
Both
Sir, if
diodes
we are
reverse
considering
biased.
both diodes at ideal, sir. So we are considering both diodes at ideal.
We can take practical diode also.
Output is 5
There is
volts.
no problem in that.
Both the diodes are reverse biased.
So because of 5 volts, the voltage of Z will be somewhere between 4 and 5.
Yeah, how much it will be? Okay, first of all, first question. Which of the diodes will conduct?
Both.
Both will conduct, because of course the P is having more voltage compared to N. Okay, both will conduct. So both are forward biased. Now, when it is conducting, what is the drop across the diode?
0.
Ideally 0.
No, practically I am asking again.
0.7.
0.7.
0.6 or 0.7 volts. Okay. Now if this is 4 volt and your drop, please mind it that it is in this direction. Now opposite of the current. Polarity of this drop or this threshold voltage is opposite to the current, right? So if you start from this point and write the KVL up to this VZ point, how much voltage do you expect? So VZ should be Vx plus 0.6 or Vy plus 0.6, because both are same.
4.6.
Understanding my point? So this voltage is coming out to be 4.6, and this is what logic? This is what state?
High.
High state.
So if we are giving high at both the inputs, what we are getting is finally a 1 output, a logic high. Correct? Now this is only one point in the truth table which we have verified. Now the other states, any other combination 0, 0, 0, 1, 1, 0, this all must turn up to 0 for this AND gate, isn't it? Yes or no?
Yes, sir.
Yes, sir.
Yes.
So let us try the next combination. Let's say I give only 1 volt over here. And I give some 4 volts over here. Now this is what? Logic 0. This is what? Logic 1. And we are trying to see what VZ is. Okay. Now tell me which diode will conduct.
Vx will conduct.
Okay.
Vy will not conduct.
What is happening to Vy?
Reverse bias.
Why do you say so?
Because if the Vx diode is conducting, then the voltage Vz will be 1.6.
Exactly.
And so
The moment this diode conducts, because of this drop of 0.6 volt, the voltage at Vz is 1.6, and the moment this voltage is coming as 1.6 over here, this is reverse biased. So this is blocking. So only one diode is conducting. This is forward biased. Now what we are getting over here?
No, 0.
1.6, and which is a logic state 0. So what happened if we are giving 0, 1? What we are getting? 0. The same would be true if you flip X and Y. Understanding my point? Or if you give both as 1 volt or both as 0 volt, this is again going to have some logic 0. So this is fulfilling the condition of AND logic. See this point?
Yes.
Correct. Similarly, we can have OR logic. So, okay, maybe here itself I can draw. Okay. Now, with diode, if we have to make OR logic, so we can make it like, with little thinking you will be able to do that. There is nothing very critical happening over here. Now, this is something which we call as our logic OR. Understanding my point? Now here what is there? Our this terminal is grounded. It is at 0 volt. So whenever you connect any high logic, let us say 4 volt. So what will happen? Diode would conduct. Understanding my point? So conducting means what? What will be the voltage over here? Again Vz will be
3.4.
3.4.
Yes.
3.4.
It will be Vx minus
Vx
0.6.
minus
Again,
0.6.
polarity you have to consider opposite to the current. So now it will be subtracted. So this will come around 3.4. So still, because 3 to 5 volt is 1, so this logic still stands for 1. So you can try the combinations like 1, 0, 0, 1 or 1, 1. For all these cases, Vz value will turn out to be 3.4. Only when you have 0, 0 combination, this voltage will be in the logic 0.
Yes, sir.
Correct? So this is how we can realize the OR circuit using the diode logic. So only diode we are using it, and we are getting our combination for the AND, OR and all these things, right? Now there is major drawback when we are using this diode logic. The first major drawback is the drop across the diode. 0.6 volt drop what we are getting in the diode, this is causing huge nuisance in the circuit. No? See, you are feeding how much? You are feeding 4 volts over here and you are getting 4.6. Now imagine if you feed 5, you will get 5.6, which is beyond your logic circuit. Understanding my point? So similarly, here you are feeding 1 and you are getting 1.6. Say for example, you connect another AND gate over here and again give this logic to this gate, and here you are giving 1 at the other terminal. Now this 1.6 with the same philosophy, it will become 2.2 volts. It has gone into the ambiguous state, in the gray zone. And if you keep on adding circuits like this, slowly it may go into high logic. So which is incorrect. Understanding my point? This additional 0.6 volt drop what is coming all across the diodes, that is actually getting added up with every circuit. So you must have some arrangement in between to bring it back to the original value. Otherwise you cannot use it. Have to have some buffer circuit or something which brings down this to again original logic, let's say 1 volt. You have to again first translate this 1.6 volt to something low logic. Then only you can use it. This is one of the major drawbacks. The second drawback is if you want to connect this AND and OR gates, these two gates if you want to connect in diode logic, It is very, very difficult again. You can try putting these two things together. It's very, very difficult to put these two in the diode logic. So that is why we move little bit further from diode. We exploit other devices which are there and which could give us the better logic design, better circuit design, and that can be utilized for realizing these and or not all these kind of circuits. Understanding my point? So you got an idea of what we are trying to do, how we are realizing this, any logic in a practical scenario. It is nothing but we are applying some voltage and we are expecting at the output some voltage. In between, the devices are operating either in on mode or in off mode, and that is what we are trying to explore. So of course, diode is not something which is universally accepted for the logic design. It is used in combination sometimes, but not alone. So that's why we move next to BJT, the next device what we are going to discuss in the class, and the combinations and or the logic based on BJT or based on transistor. So we will discuss BJT in the next class. I think next class would be on Friday, it seems. Right? Thursday is holiday perhaps, right?
Yes, sir.
Yes.
Yes, sir.
Okay. So yeah, before closing the class, so any doubts so far up to this?
No, sir.